Hello, good morning, everybody. Welcome to our final day of VGEM 2020. It's my pleasure to welcome you this morning. And what an amazing meeting we have had so far. I'm going to start with just a couple of reminders. So if you have a question to one of our speakers this morning, please feel free to use the raise hand feature directly in Zoom. And we will address the questions in the order in which you ask them. Or use the Q&A functionality directly within Zoom. And our moderators will get to those questions as well. Please note that all of the questions, as well as the talks themselves, will be recorded. So be mindful when you're asking any questions. And without any further ado, I'm going to pass the microphone over to Martina, who will introduce our first speaker.
Okay. Good morning, Virtual GEM. My name is Martina Giulidou. I'm from Johns Hopkins University Applied Physics Laboratory, and I'm the research area coordinator for magnetotailing plasma sheet. And today it's my great pleasure to introduce Dr. Barry Mauk. Barry got his PhD under Carl Markowayne at the University of California at San Diego in 1978. He then went on and flew X-ray imaging balloon payloads in northern Canada as postdoc under George Parks at the University of Washington. Later, he joined the Johns Hopkins University Applied Physics Laboratory in 1982 under Ching Meng. And his plan was to work on Earth magnetospheric dynamics. And he worked a little bit on that, but he then met Tom Kremidis, and he joined the Voyager mission as Voyager was on his way to Uranus, and that's when he fell in love with other planets. And then he went on and published papers on all of them. He has published extensively on the magnetospheres of Jupiter, Saturn, Uranus, and Neptune, using data from Voyager, Cassini, Galileo, and Juno missions. And he's presently lead investigator for the JETI investigation on Juno. But he never forgot Earth. He was the project scientist of the Van Allen probes mission. He's currently the lead investigator for the energetic particle investigation on the MMS mission. And he's principal professional staff at Johns Hopkins APL. And he was previously group supervisor for 30 scientists over there, including myself when I was in my first 2 years of postdoc. And he's a fellow of the American Geophysical Union. And today he will be talking to us about comparative magnetospheres and auroras. So I will pass it over to Barry.
Okay, thank you very much, Martina. Can you hear me?
Yes, we can.
Okay, I will share my screen if I'm able to. Bring this over and full screen mode. And I assume you can see my screen now.
Yes.
Okay, very good. I was asked to talk about comparative magnetospheres, but I was also told that people might be interested in what Juno was finding out about Jupiter. So this is sort of a mixed presentation, so I hope it holds together. I spent a lot of my career studying comparative magnetospheres. The magnetospheres I have looked at are along the top here: Earth, Jupiter, Saturn, Uranus, and Neptune. This is a chart showing a lot of the parameters for these various magnetospheres. The only thing I really wanted to point out here is something that you all know very well, that the solar wind parameters get weaker and weaker and weaker as you move outward from Earth toward Jupiter, Saturn, Uranus, and Neptune. And for that reason, the solar wind plays a much less important role in the outer planets than it does for Earth. And this is the way Tom Hill has represented that change. On the left, this is a very familiar presentation to you, the flow patterns within the Earth's magnetosphere driven by the solar winds. When you get out to Jupiter, though, that solar wind has much less influence. And Jupiter is the prototypical rotational powered magnetosphere, whereas Earth is the prototypical solar wind powered magnetosphere. I used to say solar wind driven and rotationally driven, but I now use the word power because even at Jupiter, solar wind has an important role, which I won't be talking a lot about, but the word powered is appropriate for these Jupiter as well as for Saturn. So this is one very important difference between Earth and the outer planets. Solar wind driven, rotationally driven. Another very important difference is the presence of satellites. All of the outer planets, Jupiter, Saturn, Uranus, and Neptune, have satellites that are embedded within the important magnetospheric populations. These satellites represent important loss processes and are critical for understanding how intense the radiation belts and other populations can get within these environments. This plot on the left is from Uranus, and you see these large chasms in the particle population generated by the satellites Umbriel, Ariel, and Miranda, for example, in the middle magnetosphere. Saturn is similar. It also has the rings, various small satellites in here, and very important Enceladus region. So again, these satellites are in the outer planets are very important loss processes. But even more important is that these satellites are important sources of plasma. And these sources of plasma are absolutely critical for tapping rotational energies in a rotationally driven magnetosphere. So at Jupiter, you have Io with the volcanoes that I assume most of you are familiar with, spewing sulfur and oxygen out into the environment. These volcanic plumes are gravitationally bound to Io, but by interaction, sort of a bootstrapping interaction with the surrounding environment, a lot of that material escapes, gets ionized, and becomes an important constituent of the magnetosphere at Jupiter. At Saturn, it's Enceladus with these water plumes that are coming out of the cracks in the southern part of Enceladus. These tiny moons are absolutely critical. The materials they generate are absolutely critical for explaining why Jupiter, for example, is the most powerful magnetosphere in the solar system. Without Io, you would have a very quiescent environment. The crisis that Jupiter has in all of these materials, it has to get rid of all of these materials that are being generated by Io. And so it needs to transport those materials outward. And in the process of doing so, it generates a current system that you see here that has some similarities to a current system that you might see at Earth. There are controversies about the processes by which these currents are generated. If you write the standard guiding center currents for perpendicular currents within the magnetosphere and then jump into a rotating plasma frame, you will get various familiar terms, pressure gradient, pressure anisotropy. You'll get a centrifugal force, and you will also get a Coriolis force, which would not be familiar to people looking at Earth's magnetosphere. This radial current moving outward is in fact a Coriolis-driven current. Conventionally, people have thought that the currents that go into the page here that are generating these large distortions in the magnetic field are centrifugal, but much more recently we have found that the pressure gradient and pressure anisotropy terms are probably more important in here. And so it's a real mystery how these rotational energies are tapped in order to generate these very hot populations that generate these pressure-driven currents. One of the another mysteries about Jupiter is Jupiter obviously rotates at a rock-steady rate. From the perspective of the time variations that we're used to talking about in magnetospheres, the source population is just an absolutely steady source. So you would expect this to be somewhat of a time stationary picture. Instead, Jupiter is a very, very dynamic system. This is just one example where in the Jupiter's inner magnetosphere, you see these multiplicity of what we call injections, very similar to injections at Earth. These are the energetic ion populations. These are the energetic electron populations with the energy scale inverted. And you see time dispersion in these things. And the explanation is in this cartoon here, where you have injections of plasma over confined regions in azimuth. And then you get a dispersive drift to a spacecraft like Juno or Galileo or that sort of thing. These Jupiter is dynamic over multiple time scales. There are interchange events that have minute time scales. There are injections like these that have hour time scales. And then there are storm time periods that sort of last for days, maybe 3 days, where this happens to be a storm time. Other people call them energetic events. But even though Jupiter is powered by steady rotation and an almost constant source from Jupiter, it's a highly dynamic places. Very interestingly, these injections can be seen actually in the auroral imager as very isolated patch-like region. This is a nice auroral image from Juno, Randy Gladstone's instrument, where using multispectral imaging, you can actually infer the energies of the different populations. You see the low energies in white racing ahead of the high energies in red, for example, with the same energy time dispersion that we see in the particle population. So Jupiter, despite being powered by a rock steady source, is a very dynamic place. When you compare the 5 different magnetospheres that I've talked about, Earth, Jupiter, Saturn, Uranus, and Neptune, it is Earth and Jupiter that are absolutely unique in having the most robustly energized magnetosphere. These are ion populations, the most intense ion populations that we see in these magnetospheres. And it is somewhat a surprise to me that below 1 MeV, Earth is king. It has the most intense ion populations of any of the planets. Jupiter is king above 1 MeV, where it has very energetic ion populations with much higher energies. These populations are in fact in a saturated state. They are as intense as you expect these magnetospheres to achieve on the basis of the Kendall-Petchak, differential Kendall-Petchak limit that I don't have time to go in. The other magnetospheres all have populations that are far less than their potentials. They are not saturated distributions at all. And so in that sense, Earth, the prototypical solar wind-driven magnetosphere, and Jupiter, the prototypical rotationally driven magnetosphere, are unique in the energies that they are able to achieve. Saturn is kind of a puzzle in that it is a very, very dynamic thing. This is a pass through the magnetosphere, and you see all these multiplicities of injection type phenomena. But because of all the gas and dust that exist in Saturn's magnetosphere, the populations are grossly diminished by all that gas and dust. The gas that is generated by Enceladus, for example, does not get largely ionized, unlike the gases that come from Io. So Saturn is is sort of a diminished place because of all this gas and dust. And I'm not going to talk about Saturn any further here. I'm going to talk about the polar regions of Jupiter and some comparisons with the polar regions of Earth. These are the nice auroral images that I was talking about that Randy Gladstone's instrument generates on Juno. The total intensity version here was generated by Bertrand Bonfon. Randy likes to show these multispectral images where red corresponds to expectation for very high energy particles, white intermediate, and if you see some blue and greens here, those are much lower energy. It's just a fantastic instrument that he has flown here that allows you to see all of these differences. The Juno mission, some may be familiar. This is a picture, a schematic of the spacecraft. It's the first solar-powered spacecraft that has flown to an outer planet region. It was funded by the Planetary Division of NASA. And so it's just amazing how many wonderful space physics instruments are on board. In fact, the majority of instruments, in fact, on board are space physics instruments, allowing us to do a lot of great work on the magnetosphere of Jupiter. I wanted to highlight those instruments and the people involved. Juno has a magnetometer instrument led by Jack Canerney. It has a WAVES instrument led by Bill Kurth. It has a plasma sensor, now led by Frederick Allegrini, but developed by Dave McComas. It has an ultraviolet spectrograph instrument that does UV auroral imaging by Randy Gladstone. It has an infrared auroral imaging instrument led by Alberto Adriani from Italy. And it has a radiation investigation using various assets on the spacecraft led by Heidi Becker on JPL. These are all wonderful instruments. They're advancements from previous instruments that have flown to the outer planets, But what is really, really unique about Juno is its unique orbit. It's a polar orbit that passes through the auroral acceleration region, much like FAST did at Earth. And that is really what makes Juno a unique mission. I wanted to start doing a little bit of talking about comparative aspect between Jupiter and Earth. I've already talked about this current system at Jupiter. I've not emphasized the fact that to 0th order, this is a rotationally symmetric system. So so if you take this pattern and rotate it all the way around Jupiter, you get this magneto disk that people talk about. Jupiter isn't perfectly azimuthically symmetric. There are features in the aurora people attribute to magnetotail, but to 0th order, it's a rotationally symmetric system. Unlike Jupiter, unlike Earth, this is a sunward view from Cowley et al., where you see these pairs of currents, much like we see the pairs of current Jupiter. But of course, there's this gross asymmetry where you have this up-down, down-up asymmetry associated with the asymmetry generated by the solar-wind interaction. And of course, at Earth, there's the importance of the currents generated by the magnetotail, which of course generate additional asymmetries within in the magnetosphere. So in this sense, in terms of the symmetry of the system, Jupiter is in fact a much simpler system. And of course, what Juno has been doing has been studying the response of the plasmas at high altitude to these currents. And in fact, there's no reason to believe that the response that we get up in these high altitude regions is going to be any different. Even though the currents are generated by different processes, the response of the system to those currents in principle maybe ought to be very similar. And so, of course, when we flew Juno to Earth, our expectations is we would see a lot of Earth-like phenomena. I thought I'd just take one slide to sort of review what we expect in the aurora. This is, of course, data from the FAST spacecraft. It's after Carlson et al., the special issue of GRL 1998. A lot of great summaries in the ISSI book by Poshman et al., also in a Space Science Reviews. This is an auroral image by the Polar spacecraft, I believe, and this is the trajectory of FAST flying through that auroral region. And of course, you're all familiar with the fact that in the upward current region identified by this deflection in the azimuthal magnetic field, you typically see this inverted V distribution where you see a roughly monoenergetic electron distribution thought to be generated by an electrostatic downward acceleration. And this is thought to be the main response, the main auroral driver for those coherent upward current regions. You then can go into a downward current region where you get complicated particle distributions, but we do not and have not seen substantial auroral emissions from this region. In fact, in some cases, people have identified what they call as black aurora in these regions where there's essentially no auroral emissions at all. And then sometimes in the more poleward region, you get what's a broadband acceleration region, which people also call aphanic, which no longer do you have the mono energy, you have a broadband distribution. The downward intensities are greater than the upward intensities, but you can indeed generate substantial auroral intensities associated with that aphanic region. Let me just say at the outset that at Jupiter, we talk a lot about broadband acceleration. We're a little reticent to call it aphanic, because that is presuming a mechanism. And in fact, we're seeing evidence that aphanic waves are not the only story that is needed to tell in order to understand the broadband acceleration that we see at Jupiter. So what do we see at Jupiter? Sometimes we do see things that are very familiar on the basis of the FAST and other mission results. We sometimes do, when we cross an auroral feature, we sometimes do see these nice inverted V distributions. In fact, at Jupiter, they tend to actually look like inverted V's rather than inverted U's. And so we see, in this case, you see an electrostatic potential of 100 kilovolts in this case. We see electrostatic potentials up to about 400 kilovolts, which is a good order of magnitude higher than we've ever seen at Earth, I believe, unless somebody tells me differently. But one of the differences between what we see here and what we see at Earth is that the downward energy fluxes are not at all dominated by the inverted V. This is that same panel that I showed you last time with these inverted Vs. But what you see nearby are broadband distributions. And you can see during the inverted V distribution, you get a moderate downward energy flux associated with that. Here, it might be peaking at 100 milliwatts per meter squared. But when we get to the broadband region, it goes up by about a factor of 5. And this is typical of Jupiter, that the broadband acceleration is gives you much more intense auroral emissions than do the inverted V distributions. And that's quite a different from the Earth situation. When we first published this result, we did see this sort of evolution from inverted V distributions up to these broadband distributions. And we hypothesized that there might have been an association between these, that these inverted V distributions are evolving to a broadband, which is just the opposite of what theorists at Earth talk about, where they think things start as an alphenic distribution, and as the dynamics settle down, you end up with an inverted V type distribution. Well, this association between the inverted V and the broadband was made much more explicit in later orbits, where here's an example where we were crossing these auroral features here, where we saw the start of an inverted V distribution going up to 200 kilovolts, and then suddenly turning into a broadband distribution. And it's almost like this inverted V became unstable. So you have this inverted V distribution that evolved into a stochastic acceleration or a broadband acceleration. And again, just like before, the downward energy fluxes were quite robust during this particular inverted V, but in fact came substantially higher once you got this broadband distribution. And this broadband distribution is not like Earth, where sometimes you see an expansion to lower end. The critical thing, you're getting much higher energies during this broadband disruption. This particular region, we sort of make a schematic of that here, where we think we have an upward current. You sometimes have inverted V distributions and sometimes not, but you primarily have downward acceleration in this region, whether that downward acceleration is electrostatic or broadband. The additional surprise at Jupiter is that we see very intense auroral emissions in the downward current region. And I'll show that in the next slide, where in this particular case, again, in this similar region that we were crossing before, we see a downward proton inverted V. So the electric field in this case is downward, and this is up to 300 kilovolt downward. But at the same time, you see downward electron intensities that give you downward energy fluxes that are as bright as we've ever seen at Jupiter. This happens to be 3,000 milliwatts per meter squared, as bright as we've ever seen in the Jupiter system. I do know, talking to Cindy Cattell, we see at Earth downward inverted Vs similar to this, up to about a kilovolt, I think. They tend to be in the equatorward portion of the auroral regions, but never, I think, have we identified those downward inverted V with very, very intense downward electron distributions. What seems to be happening is you have a downward current, sometimes having a downward inverted V, proton inverted V, but you essentially have bidirectional electron acceleration, with the upward acceleration being stronger than the downward, but the downward part of that being sufficient to generate the most intense aurora that we ever see at Jupiter. And this is quite a surprise based on our expectations from Earth. These different regions, by the way, do organize themselves in a fashion that I've made schematic here. This is, by the way, this particular passage is in the southern aurora. So unlike the diagram I'm showing, we're actually starting at the equatorial region and passing through this region. And of course, you start with trapped electron distribution. This is a pitch angle distribution. This minimum, by the way, is a shadow. The magnetic field is so strong that the gyro radius are small, so the spacecraft is actually shadowing itself. But what you see is a trap distribution that is being scattered into the loss cone. And these are the red here is the downward energy fluxes, and the black here is the upward energy fluxes. And due to that scattering of these populations into the loss cone, you get a diffuse auroral region that is giving you some diffuse aurora that you see in this region here. But as you go further to higher latitudes, you run into what we are now calling a zone 1 region, where where you have intensities within the downward loss cone that are more intense than the trap population now. You have an empty upward loss cone, and this zone 1 includes the sometimes inverted V, but also includes the broadband distribution that I talked about before. So all of this region here is in this zone 1, which we think is an upward current region. As you go further poleward, you run into what we are calling zone 2, where the upward energy fluxes are actually greater than the downward, but in fact, the downward energy fluxes are in fact sufficient to generate very, very intense aurora. And our thought that these are associated with specific upward or downward current regions is justified based on the wonderful work that Stavros Kotsiaris has done, who's a part of Plenari's magnetometer team. The magnetic field at Jupiter is so strong that it is much harder to pick out the azimuthal perturbations associated with auroral currents than it is at Earth. And you can't just plot the data, you have to work at it quite a bit. And here's one example where Stavros has done a great job of showing the azimuthal perturbations in the magnetic field. Here is an upward current region, here is a downward current region, and that upward current region is clearly associated with a zone 1 acceleration, with downward energy fluxes exceeding the upward energy fluxes. But as you go further poleward, you run into a region 2, which is a downward current region, but still very sufficient downward electron energy fluxes. This one happens to be associated with a downward proton inverted V as well. And you can see that double structure in the aurora. This is a zone 1 of upward current. This is a zone 2 of downward current, where this zone 2 is much more energetic than the zone 1 region. In this particular case, the zone 1 downward energy fluxes are greater than the zone 2 downward energy fluxes, but that certainly isn't always the true. In this particular case, almost everything is a downward current, zone 2 current. In fact, this is that auroral crossing here, where essentially here's the diffuse aurora, but essentially all of this auroral emissions that you're seeing here are in a downward current region with bidirectional electron acceleration, where the upward energy fluxes are greater than the downward energy fluxes, but the downward energy fluxes are still sufficient to generate very, very bright auroral emissions. I wanted to point out that there's been some, this mission is in early phases. We're still trying to get our different data sets together. Bill Kurth has done a great job in analyzing this inverted V that I showed you earlier, where you have a downward electron inverted V that converts into this broadband acceleration. What Bill showed was that during that conversion, there's a very intense portion of electromagnetic waves associated with that. This is the spectrum, where anything below the proton spectrum you might attribute to alphanic distributions, but a lot of this spectrum is above the proton distribution, and Bill has identified it as Whistler waves. And so we do believe that at Jupiter, Whistler waves are playing a much more important role in participating in the energization processes. There still may be alphanic components, but the Whistler waves, and I'll show additional evidence of that also. I'm the sort of leader of the energetic particle instrument called JEDI, and so I've been focusing more on the energetic particles, but the low energies also play an important role. Typically, Frederick Allegrini has written a wonderful paper where he has combined the plasma data with the energetic particle data, and has indeed determined that the most intense auroral intensities do indeed come from particles with energies greater than about 50 keV, much higher than what generates the aurora at Earth. But there is a very, very important role for the lower energies. What Frederick has found that even though these, by the way, these green is the auroral brightness determined by Randy Gladstone UVS instrument, and the red is the downward electron energy fluxes. This is the partitioning of that downward energy into different energy bands, where this is the greater than 100 keV part, this is the 30 to 100 keV, and this is the this is the 3 to 30, and so on and so forth. There is always a region, Frederick finds, where the lower energies do dominate, and you can kind of see this in this wonderful image that Randy Gladstone did, which is an average auroral image of the, I think it's the first 16 orbits in the northern, where you can see the regions of energetic plasma in red, both in the equator region and the polar region. But there is a region of blues and greens here where lower energies are playing an important role. And why Jupiter has this energetic structuring is not well known, but Frederick has done a great job in documenting that, that feature. I'm going to talk about another unique aspect of Jupiter's polar region, and that is the polar cap, which is the region that is poleward of this main aurora that I keep talking about. If you look at Earth, this is a nice image that George Clark generated. While we all know that there are sometimes important structures within the polar cap, theta aurora during dynamic event, typically you have darkness in this polar cap region. Same is true at Saturn, where it's a dark region. At Jupiter, very often you'll see a great deal of brightness in this polar cap region. Sometimes a great deal of that brightness is what we're now calling the red aurora, and the use of the word red is based only on these false color images, not any redness that we see. This redness suggests that it's very, very energetic particles that are generating this this aurora. But in fact, when we fly the spacecraft over this region, we have yet to see those energetic particles in a downward sense that are generating this aurora. It's a real mystery. Randy Gladstone has hypothesized that, in fact, this is not necessarily caused by precipitating particles, but electric currents that may be flowing within the ionosphere. We tend to see this only when this region is illuminated by the sun, for example, and that's a study that Randy Gladstone is writing up, basically writing up as we speak. There are other unique features of Jupiter's polar cap region. When we fly, this is an aurora image, and of course the spacecraft is coming around. This is magnetic mapping, by the way, and we spend a lot of time within that polar cap region. What we see there almost all the time is this upward electron beam. This is, by the way, an azimuth angle, which is a proxy for pitch angle, and I use azimuth rather than pitch angle is because these electron populations would be hugging the axis here, and they're very hard to see when I plot pitch angle. So that's why I'm plotting this in azimuth. But you can see across the entire polar cap, you have this upward electron beam. This is a pitch angle plot where you see very narrowly collimated along the upward magnetic field direction. Very energetic. They're almost power law distributions extending to greater than 1 MeV. In fact, we sometimes see them extending to 10 and 20 MeV using some of the other assets that we have on the spacecraft. And this is almost always there. Sometimes we see a return. This is more intense than that. It's a very puzzling feature. I do want to say that Sadie Elliott with Bill Kerr's team has done a wonderful job in showing that these beams are the variations are very well correlated with Whistler modes, and she has some nice theoretical indications that in fact these beams are accelerated by Whistler waves. And that's another reason why we tend to not call these broadband distributions alphanic, because we're finding that Whistler waves seem to be playing a much more important role at Jupiter than has been identified, at least in the Earth's magnetosphere. Another aspect, this is sort of this first half of this plot is the same plot that I showed you before. Here's the image. This is showing both the northern and the southern part, where again you see those upward electron beams here. You see in the southern polar cap, the upward energy flux is always bigger than the downward energy flux, and similar in the south, upward greater than. But one of the other features that we sometimes seen that was discovered by George Clark was that sometimes in this polar cap region you see downward ion inverted Vs that extend up to megavolt potentials. And we're talking about 1, 3, even 10 megavolts that we see these electrostatic potentials. Sometimes those here's another example where I've modified the color bar to kind of highlight this inverted V region within this polar cap region. Sometimes we see upward electron inverted Vs also, but more generally the upward electron beams are broadband. So this is a very, very common feature. In fact, this is a nominal auroral oval for Jupiter for the south and the north. This is the south and this is the north. These red regions are where we saw megavolt potentials within this polar cap, and they clearly cover major fractions of the polar cap. This is kind of a cartoon. Normally one would be tempted to do a smiley inverted V, but because of the altitude dependence that we see in these, we are very tempted to do a frowny face electrostatic potential, thinking that these equipotentials are actually closing within the ionosphere rather than within the magnetosphere. This is not a unique solution, but it's kind of a very unique feature as compared to, excuse me, as compared to the Earth's magnetosphere. I wanted to talk about one other aspect that I've talked about at the AGU, but probably other people may not. This is that same feature where I was showing the Aurora was predominantly a zone 2 region with upward intensities much greater than the downward intensities. Those upward intensities are very, very energetic and very, very intense. They sometimes extend to greater than 20 MeV. This is a spectrum that we've derived from this upward region, and we're comparing the intensity of that upward spectra with the radiation belts of Earth and at Jupiter at various L shells, all the way into the most intense regions at L of 1/4. It's just so surprising to me that these intensities are so much greater than even the intensity of the radiation belt. I do want to point out that this is a somewhat misleading plot in that this distribution is very, very narrowly along the field line, whereas these are roughly isotropic distributions. So if you were to take this distribution, propagate it to the magnetosphere and scatter it and scatter it into isotropy, it would actually be its intensity would actually be several orders of magnitude below the radiation belt. But even so, it's kind of surprising to me just how intense and energetic these upward beams are. And again, I will say that there is some radiation monitoring on Jupiter. Some of the instruments have detectors that are buried deeply within their shielding. Here is from an instrument from the magnetometer, actually has a star camera that has a buried sensor that sees electrons that are greater than 20 MeV. This is that same region that I was just showing you that's associated with this spectrum. Clearly, this spectrum goes all the way up to 20 MeV and probably environment. It's just amazing how energetic the auroral acceleration regions, and we've hypothesized at Jupiter, this is not a published work, we've hypothesized that these upward electron beams go out to greater than 20 RE, isotropize, and then are transported back inward and are in fact the source of Jupiter's very, very intense radiation belts. We can estimate, based on our crossing of the auroral region, we can estimate a source strength and ask the question, well, if all of those particles went into the radiation belt, it would only take 1 hour to replace the existing radiation belt. If something like 0.1% of those particles went into the inner radiation belt, it would take something like 40 days. So this is a hypothesis that we're looking at, that Earth's really uniquely intense compared to Earth in particular, uniquely energetic and intense radiation belt is in fact generated by auroral acceleration. That's basically all I wanted to talk about. This is my conclusion slide. How are planetary magnetospheres different? Well, solar wind versus rotation, satellite absorption, satellite materials ejected that tap into the rotational energies. If a rotating magnetosphere does not have this ejected source, it will be a very quiet and uninteresting magnetosphere. Some of the questions that arise: why is a magnetosphere powered by steady rotation so dynamic? And we don't have a good answer for that. How are Earth and Jupiter different? Earth is obviously the prototypical solar wind, and Jupiter is the prototypical rotational powered. Both are highly energetic and both reach their energetic potentials. Both have saturated spectra within them. So they are very energetic and are reaching particle intensities that are as intense as you would expect them to be. Some fundamental differences are in how the aurora manifests itself. The aurora of electrostatic acceleration is less important at Jupiter, and the broadband acceleration being more important. That broadband acceleration isn't strictly alphanic. Whistler waves seem to be playing an important role. Jupiter and Earth are very different in their response to upward and downward currents. Jupiter is unique in that the downward current region is a region of very intense auroral energies. There are very dramatic differences in the energies involved. Jupiter's auroral acceleration reaches radiation belt energies up to at least 20 MeV, if not higher. And Jupiter also has this very novel phenomena in Jupiter's polar cap. It is not known at this point in time, and it's one of the things that we're going to try to figure out with Juno, whether there are any open field lines in Jupiter's. Much of Jupiter's polar cap is probably closed. There are some regions that people think might be open to the interplanetary environment. That is unproven, and we still need to determine that. And that's everything I had to say. Thank you much for your attention.
Okay, thank you so much, Barry. Oh, sorry, Adam, go ahead.
No, thank you very much. Go ahead, Martina.
Okay, so we have a lot of questions for Barry. I'm not sure I will be able to go through all of them. I want to remind people that discussions will continue on Slack. Even if Barry is not there, I will transfer all your questions to Barry and I will try to get answers. And we will keep posting them. So I will start with the most popular questions. This one is from Bob Lysak. Barry, you have drawn the picture as if the Juno orbit is below the acceleration region.
Yes.
But doesn't the strength of upward acceleration indicate that the acceleration region is at least sometimes below Juno?
The answer is absolutely yes. One of the things where, as Juno goes into its extended, we're just in the process of writing an extended mission proposal. Because of the evolution of the orbit, we are going to get in later orbits, we're going to be getting to lower and lower altitudes. And one of the prime questions are we missing important parts of the auroral acceleration? So to Bob, I would say absolutely yes. And we hope later in the mission to answer the question as to whether we've really captured all of the acceleration.
Okay, perfect. The next one is from Dan Baker. The down electrons seem often to extend to the top of your ET spectrogram panels. How high in energy can you measure precipitation of electrons with Juno?
Yeah, so there's a couple of answers. Our JEDI instrument, in practice, the highest energy channel is something like 1.2 MeV. Because we have a lot of penetrators of the detector, not the side penetrators of the detector, we can deconvolve the electron spectra and maybe get up to about 3 MeV. The way we know, in fact, let me go back. The way we know that some of these features have much higher energies is from other assets. There are multiple instruments, and let me talk about the star camera on the MAG instrument, the UVS instrument, and the GERM instrument all have detectors of one sort or another that are buried deeply within their shielding. And so, for example, the ACS instrument is measuring electrons that are greater than 20 MeV. And by correlating what we see up to a couple of MeV with these observations that these other sensors are seeing, we do know that these spectra do go up to much higher energy. So it's not the greatest answer for Dan that I have, but we definitely have assets on Juno that can give us an indication that the spectra are going up to much higher energies.
Great. The next one is from Jason Dare. In what ways does the development of the Aurora resemble or diverge from the Akasofu model? Are there any references which discuss this in particular?
I lost a little bit of the first part of that question.
In what
Ways are
ways
the Aurora
does,
similar? Yeah, go ahead.
oh, yeah, does the Aurora resemble or diverge from the Akasofu model?
From the which model, I'm sorry?
Akasofu. Sorry.
No, that, yeah, the
It's the
Akasofu
Greek
model,
accent
yes.
of a Japanese name.
That is a question that I have not given any consideration. So let me the Akasofu model I know about, or at least I've heard presented many times, is sort of the stub-storm model, which is a time evolution of an initial state and evolving into other states. We do not. The Aurora at Jupiter kind of gets brighter and dimmer. And that sort of thing. So answer one is that it's difficult for us to stare at the Aurora to get the kind of evolution that that he is talking about. But there's nothing that I've seen in the Hubble images, for example, that that resemble the Akasofu type story, except there's something called a dawn storm, and at the very highest reaches of the auroral oval, there is often, you will see a real brightening that occurs at the northern edge, and it happens to be at dawn, and it happens to be a region that probably maps out to the magnetotail somewhat. And I know Bertrand Bonfant in particular has been likening this dawn storm to the present understanding, the evolution of substorm responses at Earth. I know he has had trouble with referees on that. How sure are you that this is, let me call it, an Akasofu type evolution? That's the best answer I have. We haven't given proper consideration of that.
Okay, that's great. Thank you so much, Barry. Thank you all for your questions. I will post them, I will copy them, deliver them to Barry, and we'll keep answering them offline. Thank you so much.
Sure.
All right, thank you both, Barry and Martina. I'm going to hand the microphone right over to Lutz, who will introduce our next speaker.
Let's see. Hello, hi everybody. My name is Lutz Rastetter. I'm speaking on behalf of the Methods and Validation Research Group, and I'm honored to introduce Tara Jensen as the plenary speaker today. Tara Jensen is a project manager at the NCAR Research Applications Lab. She has a master's degree from Colorado State University in aerosol and cloud formation, and 4 years towards a PhD in cloud physics and dynamics. For the past 5 years, she has been leading the Developmental Testbed Center's verification team in the development of the evaluation tools, specifically the Enhanced Verification and Diagnostics Framework that's called METplus. This framework has its roots in tropospheric weather forecasts verification, but over the past decade, it has been extended to also include applications such as upper atmosphere, atmospheric composition, and extended range prediction. Tara and her team have been working with SWIPC and CCMC to develop METplus capabilities for use in space weather model evaluation. So today she is presenting METplus, a unified verification and validation tool for a coupled modeling system. So Tara, it's your floor.
Okay, thank you. Can you hear me?
Yes.
Okay, and let me get rid of
I can
this.
see your slide too, so that's good.
All right, thank you. So yeah, so thank you, Lutz, and thank you for having me. I want to recognize the folks at both SWIPC and CCMC that we've been working with over the past year or two with regards to trying to apply METplus to space weather applications. It's an ongoing process, but hopefully you'll find some of what I'm talking about interesting. So first off, what is MET? What's METplus? Originally MET was developed about 12 years ago in response to a request from the tropospheric atmospheric verification community to have a single tool that could be used for evaluation of especially research and operational models, being able to transition the innovations that come out of the research community and transition that into operational weather prediction. We started with a small package that has now developed into the MET package that has many different pre-processing tools and statistical tools and diagnostic tools and so forth. And basically each tool is focused on being fairly focused on a particular area, and then what you would do is string the tools together very much as you would do with any other Linux type system and suite of tools. So it was originally developed to replicate and extend the Environmental Modeling Center, Mesoscale, as well as the National Hurricane Center, Tropospheric, Tropical Cyclone, Tropospheric Verification System. So our roots are definitely not in space weather, but the way that this package has been developed, we have been able to apply it to certain space weather applications. It's designed to be platform independent and extensible. We have a very strong help desk support that will actually be transitioning over to a forum over the next year or so. So that way the community can support each other. We have both online and in-person tutorials, or actually right now it's more virtual and video-based tutorials, but once we are no longer constrained by COVID, we will go back to having in-person tutorials as well. And we do have container support. So if you have a system where you can use containers to deploy software packages, METplus has that support. We have quite a few, over 3,500 international and US-based users, and they span quite a few different applications. Right now, METplus has been selected for the National Oceanic and Atmospheric Unified Forecast System verification capability, where the UFS is primarily focused on, once again, tropospheric atmosphere, but it's developing into a coupled system, which will include extensions to, the upper atmosphere, not necessarily to geospace, but at least the upper atmosphere. We are also working with my home institution, NCAR's system for integrated modeling of the atmosphere, which once again has that atmosphere at the center, but it is a coupled system. And so it does have extensions into, for example, WACMX and so forth within the NCAR framework. We have over 100 traditional statistics for both point and gridded data sets and several spatial and diagnostic methods, and those methods are growing exponentially. Once again, most of those right now are focused on tropospheric weather, but many times what we're doing, just the general handling of the data, while sometimes it's focused on tropospheric, it can actually be applied to space weather applications. So, so what is METplus itself? Well, it has MET, this big package at its core. And then it also has, database and display systems for plotting called METviewer and another package that we're developing, which is METexpress. The METviewer has a user interface for, identifying what you want to plot and then generating plots. But it also has a batch engine. So if you want to generate statistics plots behind the scene routinely, out of a cron job or something like that, you can run the batch engine as well. And then we are currently in the process of translating currently our statistics plots over to Python plotting scripts. And there is, we have this communication between MET and Python algorithms, which makes it much more extensible to be able to handle different data types and data that in the past we haven't been able to handle without having to add support to the C++ precompiled, or C++ compilable code. And then we are also looking at ways to have extensions to other different verification packages. So for the first part of this talk, I'm going to be focused on doing a comparison between some models that are at SWPC. One of them is the WAM IPE, the whole atmosphere model coupled with the ionosphere plasmasphere electrodynamics model using the WAM data assimilation system. Basically this is the extension throughout the whole atmosphere, extends our global forecast system in the US up to 600 kilometers and drives the ionosphere model and imparts terrestrial weather structures onto the ionosphere. And we're going to compare that to GLOTEC, the Global Total Electron Content model, which uses cosmic data and is also uses data assimilation. And for the purposes of the initial description here, GLOTEC will be considered the analysis or the baseline or the point of reference, or I use observation and analysis interchangeably. That's because I come from the world of short range weather, where you use a lot of observations independently and not necessarily as analyses. So WAM will be the simulation of the forecast. GLOTEC will be the observation or analysis, and we're going to pass these into the MET tools just to demonstrate some of the just out of the box capability without doing much modifications. So what was provided to us from the Space Weather Prediction Center were 6 days of data for a moderate event that occurred in November of 2017. And I'm pointing out that the cadence of the data coming out of WAM IPE versus GLOTEC, or forecast versus observations, are at slightly different time steps. The forecasts are coming out every 15 minutes. The observations are available every 10 minutes. And so we do have the ability to be able to handle those different cadences and just make sure that we're evaluating, where the intersection of those data sets are, which in this case is every 30 minutes. And then what we did was we took the data and we passed it into 3 of our tools, highlighted in yellow here. MODE is the method for object-based diagnostic evaluation. That's more of a diagnostic tool. GridStat is our workhorse of the MET tools. It computes traditional statistics as well as some non-traditional statistics that are based more on displacement errors and so forth. And then GridStat also computes the scores over the entire grid or over the entire region of interest, whereas series analysis computes those same type of scores, but at each grid point, so that you can get some kind of geospatial reference to the errors. You'll notice that the image that I have here is not smoothed and pretty like it is sometimes when it comes out of other plotting packages. This comes from our quick look data tool called Plot Data Plane, which keeps the resolution of the data so you can get a sense of truly what you're looking at from the data perspective. So for the GridStat tool, as I said, it computes traditional continuous statistics such as things like error or difference. If you're aggregating that over a sample, then that would be called mean error or bias. It can compute things like root mean square error, mean absolute error, correlations, and so forth. It also, within the same call to the tool, if you define some thresholds that define events, then it can compute categorical statistics such as probability of detection and false alarm ratio, Gilbert skill score, threat score, which is also called CSI, and so forth. And then, as I said, it also has neighborhood statistics that kind of look at a grid point and then look in a neighborhood around the point and computes things like fractional skill score. And then we also have recently added in another diagnostic tool called distance maps that I'm not going to have time to get into here, but basically it once again, it's kind of an event-driven type of measure that computes the difference between the predicted and observed or analysis fields, and then measures those distances through several different metrics. So in this example, what we did was we just kind of blindly just put WHAM, IPE, and GlowTech into the MET tool, into GridStats. And over here, what you can, first off, to orient yourself, we have red is greater than 25 TEC, total electron count. Blue is greater than 35, and purple is greater than 45 TEC. Once again, not exactly an extreme event, but you know, it was just something to kind of play around with and demonstrate that you can set several different thresholds and kind of look at your forecasts. Over on the left-hand side is frequency bias, which is defined as the number of forecast objects divided by the number of observed, number of forecast events divided by the number of observed events, where 1 is optimal. So you would want to see across an entire grid the number of forecast and observed events to be very similar and correlated. And then what you can see here is the range of number of forecast events versus observed events is ranges from 0 to 120. So what that indicates is that WHAM IPE tends to have much higher total electron count than its you know, what we were comparing it against, the GlowTech model. And it's definitely very clear when you get to higher to the higher events, like the greater than 45 TEC, where in several instances there were you know, over 120 times more forecasted events than there were observed events. And that's primarily because of, and I'll show this in another slide, it's primarily because of the contiguous field of greater than 45 that was available in WHAM IPE that wasn't in GlowTech. And then over on the right-hand side, another statistic that you may want to always consider when you're looking at categorical statistics is the base rate, which is the number of observed events divided by the sample size. So basically just how often did something actually occur? So you can get a sense of, you know, is this something that occurs fairly routinely, or is it an extreme event? If you're close to 0, then those are extreme events. If you're up near 1, then that particular event occurs pretty frequently. The dashed lines are the ones that give you the sense of what's going on with the base rate or the frequency of the events. And you can see once again, and it makes sense that you know, greater than 25 TEC occurs way more frequently than, you know, greater than 35 TEC, and similarly for the greater than 45 TEC. So just one example of how you might be able to use some statistics to help you understand what's happening within your simulations. Here's another diagram that you may or may not have ever seen. It's called a performance diagram. What it does is it's kind of a synthesis tool to show 4 different categorical scores on one diagram, because they are interrelated, and sometimes it's nice to be able to look at them all together. And those include probability of detection, success ratio, which is 1 minus the false alarm rate, the frequency bias are the lines that kind of go from lower left to upper right, and then the curved lines are the CSI. And once again, they all have this relationship. What you would want to see are your points up in the upper right-hand corner, which, you know, it would be optimal. If the points are, I'm hoping that my mouse can be seen. Anyway, apparently not. If the points are to the left and above that dark blue line, then those are over forecast events. So the number of forecasted events exceeds the number of observed events. And if it's to the right, then it's an under forecast. So the number of forecasted events is less than the observed events. Ultimately, you'd want to see, once again, those being on the one-to-one line. So what you can take away from this image is that, once again, and I should point out that all the different dots along and the line along the diagram are basically associated with the valid time for the prediction for ranging from 0 UTC, which in all cases seems to come in closest to 1 and kind of closest to the one-to-one line. And then it tends to wrap around through, 0 to 12 UTC, and then as it comes back towards 23 UTC, it tends to come back to that, that dark blue line. But what you can take away is that the red shown, which is the greater than 25 TEC units, tends to hover more closely around that optimal area, closer to the one-to-one line for frequency bias and up further towards the optimal upper right-hand corner. Whereas for WAM IPE as compared to GlowTech, that you can once again just see the high bias that seems to occur within this model. And I do have to point out that this model, these comparisons were done over a year ago, and I know that both WAM IPE and GlowTech have developed significantly since then. Okay, so here's another demonstration of how you could use the MET tools, and that is using MODE, which is, as I said, method for object-based diagnostic evaluation, which takes the two gridded fields, identifies objects, and then matches those and computes object attributes. And if we were to take a look at a field, in this case, it's precipitation over California and Nevada and southern part of Oregon and so forth. And your eye initially goes to, at least my eye initially goes to the green areas in Northern California and Southern California, both in the forecast and in the analysis or obs field, where even there's some reds, which is higher precip down in California, in Southern California. So if we were to apply some thresholding and some smoothing to make objects out of this, and in this case, we applied a threshold of greater than 1/4 of an inch in 6 hours, which is considered to be at least something that forecasters want to pay attention to in the world of tropospheric weather. And if we use a smoothing radius of 5, so the tool goes in and kind of smooths the entire field first with a radius of 5, and then does the threshold greater than 1/4 of an inch, then you would wind up with these objects. And through the process of merging objects, you'll see that there's like a cluster of objects based on the criteria that I put into the config file. Some of these objects were merged together into a cluster. And then matching, which is highlighted in the colors. So the red objects were identified by MODE as matched objects between the forecast and the obs or analysis field. And same thing, that there's this cluster of green objects that were matched between the two fields. And then there's also a couple of objects that we would consider from the categorical perspective as misses because they were in the observed field but not forecasted. And there were no forecasted events that were not observed, so there were no false alarms. So this kind of gives you a sense of how those objects are formed. And then once you have those objects, in this case where the forecast field is in this green and the analysis field is in purple, there are a lot of attributes. These are just 3 examples of the attributes. For centroid distance, where 0 would be optimal, you would want those 2 objects to be as co-located as possible. Or if you have non-circular objects, you might want to look at the difference in the axis angle. Once again, you would want them to be oriented the best you can so that their axis angle is small, so 0 is optimal. Or you could look at the area ratio between the two forecasted, between the forecast and the analysis object to get a sense of whether some of that frequency bias, that overprediction or the underprediction that you're seeing, is coming just from the fact that, that the one field is just over predicting the spatial extent of that particular event. In this case, you would say that there definitely is a forecast over, an over forecast because the green area is, you know, much bigger than the purple area. So that's just giving you a sense of what those attributes might mean. So here's what the WAM IPE and the GlowTech data looks like if we smooth with, I think, once again, a convolution radius of like 2 or 3 and apply a threshold of greater than 35 TEC units. And you can see that even at greater than 35 TEC, while the objects start out about the same size, the WAM IPE holds that total electron count for longer than what the GlowTech holds, greater than 35 TEC. And this is even more evident in the greater than 45 TEC instance, where the red dots, you know, the red objects that are at the bottom part of the screen are what are considered to be matched objects. And then the blue ones, once again, are things that are in one field and not in the other and unmatched. And you can see just how different the two fields are. But I want to point out that MET is capable enough, or is flexible enough so that you could actually debias on the fly these forecasts just by setting thresholds differently and possibly get a better sense once you get rid of the bias of, you know, how well the models are performing. And so through not only what we showed SWPC through GridStat and these mode tools, they were able to identify some areas of further development that I believe has decreased the bias in WAM IPE. Just to give you a sense of how you might portray things like centroid difference and so forth, you might want to use box plots to show you know, how the centroid difference changes across different valid hours. Once again, what we have is valid hours across the bottom, centroid difference in grid points across the y-axis. And, you know, red is greater than 25 TEC, purple is greater than 45 TEC. And one thing that stands out is even though the statistics for greater than 25 TEC in a traditional sense were pretty good, it does appear that there are some displacement errors that are occurring between WAM IPE and GlowTech for even like the bigger event areas of greater than 25 TEC. Okay, so then moving on to another tool, once again, series analysis tool, which computes the statistics at each grid point across a series of either time or height or, you know, whatever series you want to pass into the tools. Here's just one example of what that would look like. We're switching gears a little bit here. Now we're just looking at GlowTech and trying to understand, you know, the impacts of using cosmic RO. So we have on the top what I would consider our baseline, which is GlowTech without cosmic radial occultation integrated into the data assimilation system. And then you have GlowTech with cosmic radial occultation integrated into the system. And just because of the nature of the data, the plots over on the left-hand side are scaled from like 0 to 50 or 60. It looks like it's auto-scaling. And then if you look on the right-hand side, you can see the differences between them. And that scaling is from like -1 or -2 in the blues up to, you know, 3, 4, 5, 6 in the reds. But in essence, what you can see is the differences are occurring in places where there are no ground-based sensors and where all there is you know, some kind of input from radial occultation. So additionally, other tools in future work, we've been working with SWPC also on doing some work with trying to do masking of around regions of interest, as well as using data masking. I'll show that in a second. I just want to point out that we, some of the other capabilities that we also have. So I'll just kind of cruise through this really quickly. So we have lots of different ways of identifying masking, and the tool we use is called GenVX which stands for Generate Verification. VX in at least the tropospheric verification world is VX, and mask, that just pretty much means, you know, a region of interest. And so we have very standard types of identifying those regions of interest, including just providing a list of latitudes and longitudes or something like that that you would want to have as a masking region. You could just specify a box. Say, for instance, you just want to look across the tropics, and or you want to look from like -20 to positive 20, or -80 to positive 80, and leave the Arctic regions out, and so forth. You can do that. If you want to, you know, specify a particular circle around, like, for instance, a storm, or follow a track, which could possibly be, you know, like a big TEC event or something like that. You could do that. We also have the ability to do masking based on just a predefined grid or data, such as quality control flags, or, you know, terrain or something like that, latitude and longitude bands. And then what's in the lower right-hand corner is an example of moving solar altitude mask that could provide you with day-night masking, which once again for things like TEC could be quite interesting and useful. Here's one example of what we played around with the data set, just to demonstrate the utility of using these masking regions. We worked with SWPC, and they defined for looking at TEC with and without radial occultation, you know, trying to understand the impact of that RO based on how many other ground-based observations were available. So their quality control flag, which is across the x-axis at the bottom, range from 0 to 5, and that is basically defining the number of voxels that are passing through a grid point of, you know, voxels from the grid-based observations. And then what we did was we compared the difference between with and without radial occultation, you know, stratified by all these different quality control flags. And in essence, looking at this downward trend from QF equals 0, so no ground-based observations going through the model versus, or through each grid point versus 5, you can definitely see that there is a difference. Radial occultation does make a difference in the data. And we're still working on trying to identify, you know, is that a good difference or a bad difference? But at least we know that there's, you know, some kind of difference that is being imposed by the data assimilation of the RO. I also want to mention that we do have ensemble-based and probabilistic evaluation, things like, you know, rank histograms if you have ensembles, and Breyer score, and continuous rank probability score, CRPSS, and so forth. ROC and reliability diagrams also. Space Weather has helped inspire a tool that actually is needed by many applications, not only for the subseasonal to seasonal, that's the S2S that I have here, and CAMP is convection allowing models, so those are in the tropospheric weather environment, but S2S can also take advantage of some of the upper troposphere predictions. Anyways, one of the things that we noticed when we were looking at TEC and working with SWPC and CCMC is that they noted that, you know, clearly there's peaks near the tropics, and then up near the poles, it's definitely a little bit, you know, the values are smaller. But if you wanted to look at, you know, all those values from a global sense, possibly without even doing masking, then you may want to have the ability to use something like percentile thresholding. So say you want to, instead of saying a very distinct event is greater than 35 TEC, what about if you say the event is greater than 50, you know, the 50th percentile of the climatology for that data. So this tool, Grid Diag tool, helps compute those climatologies and identify those percentile values, and that can be then passed back into MET for use. So we're working to demonstrate that capability as well. And then only have a couple more minutes here. This is something that CCMC provided me to really kind of think outside the box and start thinking about things not totally associated with the Earth and more with geospace, and things like coronal mass ejections. And two things from this image that catch my attention is, one, on the left-hand side, in essence, you've got a plane of data, and then you have these observation points like Earth and STA1 and STA and STB, and so forth. And wouldn't it be great if you could evaluate, some of these fields on the actual plane of data? But also, wouldn't it be interesting to be able to evaluate the time series that's over on the right-hand side that shows the magnetic wind, the solar wind? And I think that we should be able to do that with MET. So for the evaluating the plane of data, there's a framework in there called HIRA, which was developed by MET back in 20. In essence, it's another neighborhood-based method. You maybe have 2 or 3 observation points in this plane of data, and you can use the neighborhood methods to look in, within a user-defined neighborhood of that observation point, and to look for events that are identified by thresholding and so forth. And if the events occur within the neighborhood, then you consider that as something that occurred close enough to that observation that you may want to count it. So this allows for some spatial and temporal differences. For HIRA, what we do is we, in essence, turn that into a probability and then compute a Breyer score. And then that can be compared to probabilistic fields as well. So that's one area that we would like to continue exploring to move into geospace. And then the other area is just evaluating time series forecasts. In the past year, we have added in the ability to have to be able to read in any a time series forecast and a forecast and observations that match pair record in a format, whatever format it is written out to, and it doesn't have to be in a MET format anymore. Using a Python script to read in the time series and format that and then pass it into the MET tool. The MET tool that you would pass that into a stat analysis that would compute all the traditional categorical statistics that you would like. And then you could pass that output either to our METplus plotting tools or to your own personal favorite plotting tool. So that's another area for demonstration and exploration in the very near future. And then finally, the other thing that I noticed here are the peaks in solar wind highlighted by the gray arrow. And you can kind of see that there's like a low point and then a peak in the solar wind. And that really resonates with me. It looks like something similar to what we see with tropical cyclones and actually renewable solar winds and so forth. It's called a rapid intensification event. So say, for instance, you have a definition of an event that is defined by a change in intensity, in this case 30 knots of wind speed over a 24-hour time period, and you want to compare between whether it was predicted and observed. And so the blue box and the red box show the areas of temporal areas of rapid intensification. And in this case, it would be a miss because those 2 boxes don't overlap. They didn't occur at the same time. But many times, if you can predict that event within pretty much the same temporal range then as what is important to the end user, then it could still be a good forecast. For example, a CME, if you can predict that impact within 30 minutes to an hour, that could still be a good event. If you can't predict it, it's like predicted 12 hours in advance, then maybe it's not a good prediction. So we do have the flexibility to define a window over which those events occur, so that then, if it's something that's meaningful for your users, then it can be considered a hit. and you can change the computation of your categorical statistics. So we also apply these to things like renewable energy ramps, wind events that either increase the energy or decrease it, or solar energy, the cloud events or something like that. And I think that it could be applied to also solar wind for CMEs and magnetic fields and so forth. The final area that I think is really easy, low-hanging fruit to go after with current space weather prediction is aurora forecasts, and using mode to both identify the outer ring edge and the actual location of the aurora, as well as identifying the inner ring edge and looking for the expansion around the magnetic pole. And in talking to people at CCMC and SWPC, they both felt that would be kind of interesting to explore. So we're hoping to explore that soon. And that is a very quick overview of some of the ways that you might be able to use METplus. I want to say thanks at this point and answer any questions. But here's also some links on how to get help and how to get the METplus package, and as well as where some precompiled installations are available within at least the US high performance computing environment, both for academia and for NOAA. And thanks to NESDIS and NASA for supporting the work that we've been doing with space weather. Thank you.
Okay, yeah, thank you, Tara. Yeah, there was a very detailed description of the wealth of tools and methods that are available in weather forecasting and climatology. And SWPC and CCMC are currently working on making those available for the space weather community. And so we have a few questions, and we're still opening up for more questions. So I have one question from John Hajdúček. So the examples that you have shown so far tend to use 2D data on a geographic grid. So, and you mentioned some other things, but does MET also work with 3D volumetric data?
At this point, it does not. It is in our plans for development, and it's actually in talking to both CCMC, so like you, Lutz, and others. We finally feel that we have data sets to actually start working towards that support. That's a pretty big change in paradigm. We've made our first inroads into support for that over the past year. I'd say that it's probably at least another year and a half out before we have full support and can really make that available to the community. Sorry. So right now you pretty much have to, we have to figure out a way to make it, a 2D plane out of the data.
Okay. Yeah, and another question going in a similar direction is, what about vector fields, like directions of flows and wind speed and stuff like that?
So we do have some scores that take into account vectors. For us, it's wind direction, and so we already have that support. We might have to actually see what the data looks like and iterate with the folks that are interested in those vector fields, just to make sure that if we don't have the implementation that we need, that we can fully understand what they're trying to accomplish and figure out a path forward. But we do have things like you can compute vector statistics, at least for wind.
Okay, yeah. So there was one person also mentioned like multidimensional. It's like I think we have space and velocity space. It can be like 6-dimensional or something, displacement and stuff. So that'll be something to work on in the future.
Yeah, that's once again. I mean, we've been tied to the Earth for 12 years now. So trying to expand our horizons into your space is it'll take a little bit of thought.
Okay. Thank you. Are there any other questions? Anybody?
Sorry, Liz, I think we'll have to stop there if there are additional questions.
Okay.
So thank you very much, Tara and Barry. for two wonderful talks. And I'm just going to pass the microphone over to our chair, Vanya, for closing remarks. Thank you.
Thank you, Adam. So yes, before we finish, this is our last plenary session of this virtual GEM workshop. So I would like to take a few minutes to thank the meeting organizers, Charlene Huang and Chris Muikis, who have done a fantastic job with the organization, and also the steering committee and focus group leaders who have been working very hard to make this virtual GEM happen. And I think a few months ago, we were wondering whether we should have it or cancel it. I think now we are very happy that we made the decision to have it with more than 700 registered participants. I think it's a great success. And even in a virtual platform, we can talk about the great scientific debates that we have. And we heard about the new drive centers that started. So we look forward to hear more about their inventions in the next workshop. We also started some great discussions about the decadal future and beyond, and where we would like to see GEM in the next 30 years. So we will continue these discussions online through the various Slack channels. And finally, we also started very important discussions about diversity and inclusion and mental health wellness. So if you are not on Slack, I would like to encourage you to join and to see the amazing response and support from the community on these topics that we got there. It's really impressive. So we will continue this discussion. We will post more information about available resources on the VGEM websites, and the Slack support each other channel. So this afternoon we'll continue with focus group breakout sessions. Then we'll have the poster sessions. And we will end VGEM with the memorial for Sam Bingham. So one last reminder is to upload a PDF or video of your poster to the VGEM website. So again, we encourage you to continue all GEM discussions via the Slack channels, even after the workshop. So I thank you all for attending, and I hope to see you next year in person in Hawaii.